Hello friends, myself Anil Kumar Singh. In this tutorial, I will explain power spectrum of FFT data. How to convert FFT data into power spectral density in Matlab. Okay, so just open the Matlab tool. So I have opened the Matlab tool. This is the user interface of Matlab. Here I have already coded power spectral density of sinusoidal signal. Okay. So I will explain the code line by line so that you can understand easily, and you can able to perform power spectral density. You are able to compute power spectral density of sinusoidal signal. Okay. So in first section I have written the command to clear the workspace and command window. And second section I have defined the parameter which is used for signal generation as well as performing the FFT, inverse FFT and power spectral calculation. In next section I have generated the signal x1, and next section I have generated signal x2. Okay, I have defined the frequency as 5 kilohertz and one is 4 kilohertz, 400 kilohertz. Okay, E3 means 10 to the power 3. So 400 kilohertz, here 5 kilohertz. I have defined two signal, and third signal is sum of these two signal x1 and x2. Okay, so on this signal I have performed the FFT to convert this time domain signal to frequency domain signal. This section convert this time domain data to frequency domain data. I have already explained in the previous video all these things, how to generate the signals, how to perform the frequency, how to convert time domain data to frequency domain data using FFT. In this section, I will explain how to compute power spectral density. Okay, so this is the section where we are computing the power spectral density. To compute power spectral density, what things we required? Input to the power spectral density is nothing but FFT output. Input to the power spectral density is nothing but FFT output. So what is basically PSD, power spectral density? Power spectral density is nothing but mod of x of omega k whole square. X of omega is nothing but FFT output. Okay, so x of omega k the whole square we have to perform. It means, see here, this is the FFT data. So real data multiplied by real data. Sorry, see here. Real data of FFT is multiplied by real data of FFT plus imaginary data of FFT is multiplied by imaginary data of FFT. It means imaginary square plus real square. This is nothing but power spectral density. Okay. So first section to compute the power spectral density, and then next section do the logarithmic of this power spectral density. It means convert linear data to log data. Okay, so this code solve the when power spectral density is 0, that situation can be handled by this section of code. Okay, and output of this section of code will be going to the 10 log base 10 log temp input 1. This one is just I am taking the logarithmic of this power spectral density data. Okay, 10 log base 10 PSD to convert linear data to time domain data in DVM. Okay. So how this section handle the zero set? If log base 10 0, this is undefined. So to avoid this undefined condition, we have to set, see, if power spectral data is 0, then instead of 0, just copy this some finite value, so that log of some finite value which is not undefined. Okay, in this way we can manage we can resolve the undefined logarithmic data. Okay, in this way we can perform power spectral computation on FFT data, and also convert linear data to the logarithmic data. Okay, once after computation of power spectral density, just plot it here. Just plotting, I am plotting here n values and power in dVm. What is n values? N value is nothing but frequency axis. This is computed from the FFT. See here, n value is nothing but minus NFFT by 2 to NFFT by 2 minus 1, and just simply multiplied by frequency resolution, sampling frequency by NFFT. This is nothing but n values. This is the variable which is x-axis value. Okay, and I have titled as power spectral density of mixed signal or sinusoidal signal. Okay, and x level I have marked as negative and positive frequency, y level marked as power spectral density in dVm. Okay, just Control S to save it and just do the simulation. First change the folder and do the simulation. Okay, I have generated 5 figures. Just I am rearranging and then I will explain all the outputs. See, figure 1. Figure 1 is sinusoidal signal. Figure 2 is also sinusoidal signal having high frequency. I have defined here 800 kilohertz. This is 800 kilocycle per second. This one is 500 cycle per second. 5 kilohertz. It means 5000 cycle per second. Okay. And I have added these two signal to generate the mixed signal. This one is mixed signal of these two. It means added of these two signal. Figure 3. Okay. And I have computed the FFT of this mixed signal, and the spectrum look like this. See, I have just zoomed. I have just zoomed it, so we can see clearly. See, just zoom it. This section. See here, 5 kilohertz. First frequency is 5 kilohertz. This frequency in hertz, so 5000 nothing but 5 kilohertz. Okay, so one frequency is 5 kilohertz and another frequency is, just zoom it to see, 400 kilohertz. Okay, this one 4 and 10 to the power 5, it means 400 kilohertz. So I have plotted this mixed signal in frequency domain, and we can clearly see what are all the frequency in the mixed signal. Okay, next figure is power spectral computation of this FFT data. It means just I have computed real square plus imaginary square, then I have taken the log of power spectral data to compute the linear data to dVm, power in dV. Okay, so this is the plot. Y-axis you can see power spectral density in dVm. So here see magnitude level in magnitude is 0.1, but in power spectral density the level is 30 dB. Okay, and x-axis is frequency, similar to frequency domain, whatever the x-axis. Here see negative and positive frequency in hertz. Here also negative and positive frequency in hertz. Only level changed in y-axis because of I have converted this linear data to dB, into logarithmic data in dB. Okay, and these are the spectrums. In this way, we can compute power spectral density of sinusoidal signal. In next video, I will compute power spectral density of noisy signal. Okay, thank you so much for watching my video.